Good morning, everybody. Hope you're having a great day. Today we have a Code Forces round. In fact, it's educational round 124. Should be pretty fun. We'll do that in just a minute. Might be a minute or two late here. Quick announcement, though. So you may be wondering where I was for the last Div 3. You know I like conquering a good Div 3, just like anybody. And I sure do. However, my power just totally went out in half of my apartment. And unfortunately, that was the half of the apartment that includes my computer. So computer shut down, monitor shut down, and then it turns out it was because I had too many things plugged in and broke a circuit. But I didn't know where my circuit breaker was, so it was a whole ordeal. Anyway, that won't happen today, or if it does, it will be much less intrusive because I now know where the circuit breaker is. So let's jump into this contest. We've got this educational round 124 here, and some fresh problems. I need to set this up to be automatic. I did one time and then I stopped using it kind of. All right, playoff. Oh, classic. This happens so often. I don't know why people are this obsessed with this. This was in the regionals too. They had one of these problems. Tournament is held in N stages. In each stage, the athletes split into pairs. Okay, I see. Yeah, okay. What's the question? The winner of the tournament. Does the bigger one always win? Oh, if the sum is odd, the athlete with the lower index wins. If the sum is even, the athlete with the higher index wins. I see. Okay, so this winner, you're like, is it odd or even? Well, you know the sum will be, sums here are odd, and they're even. Oh, so after the first round, they're all even, right? Because after the first round, you have all odd, so then all the sums are even. So what happens if they're even? So it's just 2 to the n minus 1 is the answer. Yeah, pretty cool. You can do it Eclipse. It's a cool problem. Usually I don't like tournament problems because they're so overdone, but pretty interesting. All right. Prove him wrong. Recently your friend discovered a special operation on an integer array A. You can choose 2 indices, I and j. Set them both equal to the absolute value of their difference. For every array of n integers, you can find pairs of indices so that the total sum of A will decrease after performing this operation. It's not true. Oh, when they're all at least 1. Such that, what do you say? The total sum? No, you can't. It's gotta be right. What? What? Really? So there are no pairs that do this? Will decrease. I wonder if it has anything to do with powers of 2. So might actually have to do with doubling. You've got 1. Okay, let's say you have A and you have B. So before you have A plus B. After you have A minus B times 2. So in fact, we need this to be the bigger or equal. Yeah, so it's powers of 2. So the sum needs to be smaller, which means it needs to increase by, you need to have a, and then, well, 2a doesn't work, it's gotta be 3a, huh? So this would be, this is 2a times 2, so this is 4a. Oh, wait. Is it 1.5a? Oh, this is 2a, but this is 3a. Yeah. So in this case, you have a plus 2a, which is 3a. And then here you have a times 2, which is... What is a times 2? 2a. Okay. So what do we need? So we need a plus b equals a minus b times 2. So what does b equal in terms of a? So a plus b equals 2a minus 2b, or not 2b? That's the question. So we subtract a from both sides. Oh, I guess let's subtract a from both sides. So then we get just a. So now a equals 3b. So one's a third of the other. Yep. Okay, there's our proof. So we have 1, 3, 9, etc. Okay. Yep. So if n is less than or equal to max.size, that's out yes. And then for I equals 0, less than n is plus, it's out max.get I plus a space, and then a new line. All right, otherwise, is this out? No. Another cool problem. I really like these. 1, 3. Yeah, looks good to me. All right, on to C. On to C. Fault-tolerant network. There's a classroom. Forgot to set up 0 when my power went out. Wait, where do I have 0? Darn it, we don't have 0. No announcements, everybody. That's so sad. Isn't that depressing? Oh, man. Oh, well. All right, we've got a classroom with 2 rows of computers. There are n computers in each row, and each computer has its own grade. What is a grade? Okay, we'll worry about this in a minute. Computers in the first row have grades A1 to AN, and in the second row, B1 to BN. Initially, all neighboring computers in each row are connected by a wire. Pairs I to I plus 1 have a wire. Okay. So 2 rows form 2 different independent networks. Your task is to combine them in one network by connecting one or more pairs from different rows. So you have a bipartite graph, we need to connect them somehow. Okay. Connecting the ith computer from the first row with the jth computer costs AI minus bj. The absolute value of the difference. Okay. Yeah, I see. Okay. You can connect one computer to several others, but you need to provide at least a basic fault tolerance. You need to connect computers in such a way that the network stays connected despite one of its computers failing. In other words, if one computer is broken, no matter which one, The network won't split into 2 or more parts. No matter which one. No matter which one? It's a lot of constraints you got there. In fact, very many. Minimum total cost. Corners. Corner cases. So, yeah, that's odd. So we've got like these things and these things. So this guy's got to get connected to something, right? Because if this guy dies, we're in a lot of trouble. Yeah, so we need to connect this to someone. We need to connect this to someone. We need to connect this to someone. Do we ever not go top, bottom, or crisscross? Oh, you might go this to random guy in the middle. 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 Yeah, we can come up with our case where it's like that. So we can have like 1, 2, 3, 4, 5, 6, 7, 8. And then we can have 1. What do we want to end this with? Let's end it with a 4. And then we have some 8s here. So yeah, we can do this in 0. Look at samples. Oh wait, oh no, they have to be across networks, okay. So 25 to 10, oh, this is it, right? 25 to 10, 25 to 10, 1 to 4, 1 to 4. Yeah, okay. Okay, so what are the options? We can collect left, left. We've got left, left. Right, right. We've got left, right, right, left. Okay, so this is like both vertical. We can make an X. We can do left stays and then right is free. Then we can do right stays, left is free. And then we can do top left to bottom right, others free, and then top right to bottom left, others free. Okay, so yeah, we can just say we just want the closest, so static int min diff. So we'll just get the closest here. So this will just get the closest thing to x in an array. And then static int a int a and b turn math.abs a minus b. Okay, so int ants equals okay, so not that min of answer and a of a at 0, b at 0, plus a of a at n minus 1, b at n minus 1. Okay, this is the first thing. Then we have crisscross, so this with 0, it's fine. Okay, then we've got left stays, right's free. So plus min diff of b and a at n minus 1 plus min diff of a and b at n minus 1. It's another possibility. Oh, we could definitely just do half of these and then flip it, but this is fine. Okay. We'll just finish this up. Okay, so yeah, now we need to make these ones 0. And these n minus 1. That's this case. Okay, and then we have kind of the other one. So this is a at 0, b at n minus 1. And this is a at n minus 1, b at 0. And then we also have the reverse of this. So we have b at 0, a at n minus 1. Oops. And then we have b at n minus 1. B at 0, b at n minus 1. Oh, this is a at 0. Yeah. Oh, we also have everybody. Yeah, there's also everybody. B a at 0, a b at 0. Yeah, I think that's right. Okay. Dang it. Why? How is this negative? Oh. It's a very useful test case. Yeah. Looks good. There we go. Problem C. AC. Nicely done. All right. Problem D. Nearest excluded points. We're given n distinct points on a plane. Coordinates of the ith point are xi, yi. For each point, we need to find the nearest in terms of Manhattan distance point. Nearest, this is an odd placement of an aside. I would definitely put that after the word point, but works for me. The nearest in terms of Manhattan distance point with integer coordinates that is not among the given n points. Nearest to what? The nearest, oh, the nearest point to each point. Okay. Interesting. So Manhattan distance is sum of absolute value difference? Yeah. Well, it's an interesting problem. We know the nearest point will border one of the points in the set. We know it won't be that far away. Kind of binary search. I don't think binary search is very useful here, though. So this is like diamonds, right? It expands as a diamond shape. Yeah. I see. Thank you for saying this. Thank you for not guaranteeing. If I ever publish a Code Forces set, there will be a no guarantees guarantee. I guarantee it. I don't actually know how to do it. Oh wow, lots of people don't know how to do it. Ah, okay. I started a couple of minutes late. Wow, all right. So, I mean, obviously you can BFS. Problem is, that's too slow, because you hit lots of things that you've already hit. So you kind of need to skip all those. Yeah, if you're given a very dense diamond, then you got a problem. Oh, but you can say first thing in each direction because there are only 4 directions. Yep. Yeah, okay. So, here's the idea. Got it. So, we're going to have 2 sets of things. We'll have like some X's and some Y's. Like some different sets of X's and Y's. And they won't actually look like this because this case would be impossible, but whatever. And now, we're gonna like sort these points in some Y, or in some in some direction. So there are 4 directions, right? There's like up and to the right, up and to the left, down and to the right, down and to the left. Actually, in fact, there's only up and to the left and up and to the right, because this works both ways. Yeah, and then we'll just go forward and backward through the arrays. But the point is, the nearest thing to you is going to be in one of those 2 directions. It's going to be adjacent. It's going to be like the next Y adjacent to you in the list, and that's going to be the thing that's interesting. So static class vec, we'll say int x, y, public vec, int x, int y. We also want a group. Okay, so we have all of these, that's fine. And then we want, well, we'll do comparable later. And then int dist vec o, return integer, or return math.abs of y minus o.y plus math.abs of x minus o.x. And then we'll have an array list vec of candidates. And then I guess we also need an ID, don't we? Oh, I guess we can just use this as the group. Make the ID -1 if it's Okay. So vec array points is new vec array n. Darn it, we need implements comparable vec public int compare to vec o x not equal to that x. Okay, so tree set of vec all points is new tree set, and then yeah, for int I equals 0, I is less than n plus plus, o points at I equals new vec of this, and I. And then all points dot add o points at I. So now we'll have all of the points here in this tree set. And now for vec v and o points, so for each of these points, we'll consider int array dx equals like all possible ways we could take one step, so -1, 1, 0, 0. And then we'll consider the same thing in the y direction. So then we'll have some vec, like O equals new vec v.x plus dx. Okay, so now we'll have this new vec that we're considering. What's wrong with this? Oh, we need the ID. The ID is negative 1, this is fake. Okay, so if not all points that contains O, then we'll have some array list vec of separate points. We'll call these like B points. So now B points dot add O. Okay, so now we have our two sets of points. Yes. So now we've got the points with real IDs and with -1 IDs. Okay. So now we need these all in one set. So array list vec together equals new array list of all of them. And then we'll say together dot add all B points, and then together dot add all points. Are they gonna roast us with there being duplicates? Good. Okay, they're all distinct. All right, so now we've got all of them, and now we need collections.sort. Oh, we need, yeah. Well, I guess it's fine. Collections.sort. Together. A, B, sort by integer dot compare a.x plus a.y to b.x plus b.y, and then later on we'll make these minuses. Okay. All right. So, yeah. For int I equals 0, less than n, or less than together dot side plus plus. Okay, so then we want vec last neg equals null. Oh, we can just, yeah, so vec now equals together dot get I. I'm not doing a for each because I want to be able to copy and paste things. If now dot id equals -1, last neg equals now. So we'll store this last -1, and then we'll say else now dot candidates dot add last neg less neg not equal to null. Okay, so do the same thing. Going backwards. Okay, and then we'll do the same thing here. And then we want we want vec closest. So vec ants equals candidates dot get 0 for vec v in candidates. If dis to v is less than dis to ants, then ants equals v. So this is how we do this for each vec, and now we just want to print for each of the original points what the answer is. So for vec v in O points, this out v dot x plus v dot y. What? Single test case. Choo-choo's in the set. Well, that's a problem. Oh, yeah. 1, 3 is the same distance. Okay, well, let's just submit. Code forces can check it for us, huh? Oh no, I'm gonna need print writer. Okay, looks like we're wrong. You're kidding me. How could we be wrong? We can't be. We're right. Did they say what to do if there's a tie? If there are multiple answers, you can print any. We are printing any. What's up with you? Chillax. How could we possibly be wrong? So we're not resetting this, but don't think that matters. How is this wrong? Nobody's getting this wrong. There's no way. 37. Oh, half the people are getting it wrong. How do you get this wrong? Print the point with integer coordinates that's nearest in terms of how. How do you even, like... We get the closest one, so it's either the first candidate or where it's wrong. It's not even crashing too. If distance to V is less than distance to answer, then make the answer V. I don't know, I guess we can try this one. So 4, 0, 0, 0, 1, 1, 0, and then 1. What does this give us? 0, minus 1, 0, 2, 1 minus 1. 2, 1. That's right. Oh, what if they tie? Well, if they tie, then we'll hit them on the way back. Surely, yeah. How is this possibly wrong? I have no clue. I have no idea. I don't know. Let's move on. No idea. You guys who wrote tests are smarter than me. Let's note the size of a maximum matching graph as, wait, how many? Okay, we got EF. We have E and F. Yeah, E and F. Nobody solved E. What the heck? How? Is the idea not right? Certainly the idea is right. No, the idea is wrong. Dang it. I'm a fool. Okay. Am an idiot. Ready? A, B, C, D, E. Yep, so you've got when in reality it should be this one. Wait, no, I hit this one. I do hit E. No, I hit C and D. Yeah. Yeah, so I have X and then this guy, the two things that are really far away. Then I'll hit this, then this, then this. So this is just fundamentally flawed. We have, yeah, okay, I don't even know how to do this for if they're all in the same set. Just like for each point, get the closest point. Like how do you can't really sweep. What if they are all in the same set? We want to like, well, if we can sweep, making it work for both sets is not difficult. It's very easy. You just like ignore half of them, store your variables separately. But yeah, what do you do otherwise? Is this like, it feels like it should be a common trick. Like the diamond trick. So what is this if it were squares instead? Squares is, if the distance is squares, so then this is the max. It's the max of dy or dx. I guess you can do parallel binary search. No, not really even, can you? You can evaluate at one level. Well, it's not really, it doesn't really work. If you have a thing, what am I trying to find? It's not necessarily in any direction. Yeah, because you can have a big loop of things like this that match every direction you might want to check perfectly, but it's really this one. It's an interesting question. All right, when you don't know something, and it's probably a common problem. Nearest neighbor by Manhattan distance. This is unhelpful. Choose weights. What are these weights? Yeah, not helpful. Voronoi. Voronoi is for 2D. We don't really care. Minkowski. What is Minkowski distance? Oh, it's just like generalized. Okay. So this is like machine learning. You're given n points in Q queries. For each query, you're given one of the points in the input. You need to answer which point in the input is closest to P. Yes. Okay. Q times max of x, y would pass or not. Probably not the right idea. For every point, find the closest point. Gotta love, see, it's an educational round. We're learning during the round. Be educated. For every point, find the closest in every of the 4-part coordinate system centered at the point. Then sweep 4 times. Why does this work? Oh, well, how does this work? Okay. For every point, find the closest point in every 4-part coordinate system. In every, oh, I see. So we look at things that are up and to the right. Yeah, that makes sense. Okay. Yeah, let's implement it. Okay, so here's the idea. We need a segment tree. How big do the points get? We need a segment tree. Okay, so most of this is garbage. Yeah, we don't want everything together. Well, maybe we do. Let's just get rid of all this. This part's probably useful still. Okay, so we're gonna do 4 sweeps. The first one will be sweep by X. And then look at things with a smaller y. Find smallest x plus y. Yeah, okay. And then we need a vec root 90. I guess this will just be void. And then void right 180. Well, it should be a vec. Or 270. Lazy man's way of doing it. Okay, so return new vec. This would be y minus x or something. This might be backwards, but it's fine. Okay. All right, so we have all points. We have the b points. Okay, so then 4 die equals 0 less than 4 plus. Yeah, so now we need array list vec all points new array list. So add all b points and then add all all points. Okay. All right, so then next we'll say for vec v in all points, v dot rotate 90. Oh, we have to set it. We probably want to just do this in place. Well, yeah, we need the pointers. Okay, so int new x equals y, int new y equals minus x. So do these and then do this. Okay, so now we need a segment tree. So leftmost, rightmost, L child, R child, public ST, int L, int R. Does this work for negatives? No, does not. Because -1 needs to round left. Okay. So we need to do the classic L plus R minus L over 2. Left plus the difference over 2. Okay. L child equals new seg tree from left to mid, and then R child equals new seg tree from mid plus 1 to right. All right, and then void add vec, and then we've got void, we got vec get min x plus y. All right. Cool. Yes. So what does this do? So we've got vec v int. So we will, I guess, yeah, we'll just set an x. If x is less than leftmost or x greater than rightmost, and return. Otherwise, it is in our range. So we will say if v dot x plus v dot y. Is it x plus y? Yeah, because we're looking at this line. So v dot x plus v dot y is less than min, or okay, so if min x plus y dot x plus min x dot, or min x plus y equals null, or it's less than min x x plus dot y, then min x plus y equals x or equals v. Then if L child is not equal to null, L child dot add vec get rid of this and do it like this. So if x less than or equal to L child dot rightmost. Oh. Then we'll say okay. All right, so we've got this, and then we've got int L int R. Yeah. So if L is less than or equal to leftmost, then return min x plus y. Okay, we want static vec better. Vec A, vec B. A equals null. Return B. B equals null, return A. And then, yeah, so then we have this part. Get min x plus y for this range. Yes, okay, so if r is greater than rightmost, or L is less than leftmost, or r is, sorry, if L is greater than rightmost, or R is less than leftmost, return null. Otherwise, return better of L child dot get min x plus y, or R child dot get min x plus y. Okay, so this is fine. Good. So we have this segment tree. How big are the points? 2 times 10 to the 5th. So we'll say 3 times. Oh, wait, they're all pretty small. Yeah, that's fine. 3 times 10 to the 5th to. Yep. Yep. And then we'll say collections.sort all points by a b oh, okay, so this is going to be a bit more complicated. That's fine. We'll say if a dot x, we're going to sort by y, right? Yeah, sort by y. A dot y is not equal to b dot y. Return integer dot compare. Yeah. So sort them by y if we can. Otherwise, x with b dot x. Otherwise, sort them by x coordinate. But we want them sorted in decreasing y value. The y is decreasing. Yes, bigger y's come first. Bigger x's come first too. Yeah. Okay, and for vec v in all points. If v dot id equals -1, then st dot add v dot x. otherwise, all points dot, oh, we need closest, so vec closest equals st dot get min x plus y from anything above our x coordinate is allowed. Yeah. So we've got v dot x to big number. All right, and then we'll say this is the closest one to us. Then v dot candidates dot add closest. So now we're good. Yeah. Okay. No, not good. What is the problem? Why? Okay, and then sys out processing plus v dot x plus v dot y. Why twice? Ah, it's not right. This needs to be O point set. Yeah, okay. Seems plausible to me. Took a while. Took a solid long time, didn't it? Watch us TLE. Alright, I'm getting a Cliff Bar. It's correct though. So at this point, everybody here is waiting to see whether I'm in a rage. Job! Dude. Why do I even use Java? What am I doing with my life? That was dumb. This is immensely dumb. It's just like mind-bogglingly stupid. Like, I don't even use this. Was it the tree set? Come on. So that's something. This. Maybe we're creating things we don't. It's literally n log n. It's literally n log n. It's n log n. It's 2 times 10 to the 5th log 2 times 10 to the 5th. I'm even being smart here. There's no way they roast me over additions. That's just not possible. Maybe it's the tree set? This is dumb. Okay, so then scene.add to L O points dot or O points at I dot X O points. All right, and then we'll say if not scene.contains to L b dot x plus dx at d b dot y plus dy at d. Then points dot add new vec b dot x plus dx at d b dot y plus dy at d. Okay, so what have we sped up? We no longer use the tree set at all. We just use this hash set. Segment tree is a bit smaller. It's being cleared, not remade. We're using print writer. technically we don't need this for loop. Really should not matter. Java's killing me. So help me if we TLE. I'm gonna lose it. I'm gonna lose it. Dude. That's how you turn somebody into the Hulk in real life. Like, literally the amount of rage flowing through my veins at this is... What do you even want me to do? You want me to fix this? Remove a factor of 2? What? What am I doing? This is literally all totally fine. Literally, what is the problem? Is this divide by 2? Does this need to be array based? Is that it? Okay, there's just no way it can be any of this. Well, it's 10 to the 6. It's 10 to the 6 operations. This is fine. Guys, I'm being cheated. For those of you who use C++ and don't appreciate this, I am being cheated out of a problem right now. And even if I get the problem, I'm being cheated out of time that I really do not need to be spending in this problem. This is like patently unfair. I have the right solution. I am 100% sure this is intended. I don't know, should I just move on? Well, I'm a very unhappy panda right now. Don't like this. I do not like this. Okay, we're gonna pretend that part's fine. So, bad part's a segment tree, huh? It's twice as big as it needs to be. We can make it twice as small. If we want, we can do hacky stuff, or we can make it iterative. We can't do the bit segment tree, I don't think. Can't use a bit. But we might be able to do it similarly. Okay. Yeah, how do we want to do this? Alright, so this is dumb. It's incredibly dumb. It's like so dumb I can't even bother to tell you how dumb this is. Oh, is it the fact that these are arrays? That might be it. That could actually be it. Yeah, this could be it. Yeah, okay. All right. So now this is v at candidates, or v dot candidates at v dot candidate size plus plus equals closest. This might actually speed things up quite a bit. Because that is quite a few array lists I don't need. What? Memory limit? What? Huh? I don't believe you. Memory limit exceeded on test 1? I'm using less memory. Is it this? Wow. Wow. What is I? I'm using less what is the... What? So this is literally the same. Oh, this is, okay, so this is not actually what I want. So we want, compare this one to previous submission. Okay. Is it because we're using a hash set? No. Yeah. Well. No, this is... Compare this to the one ending in forces. I'm gonna rage quit here. This is really testing my patience. Okay, previous was... So this doesn't use any more memory. This is literally a minor change. This, we make it size 4 if we need to. That should be fine. That's fine. Why more memory? Hash set? We didn't use a hash set a while ago. There's no difference here. My goodness. It's just absolutely infuriating. I use linear memory. Literally order n. Why are you killing me on this? Memory usage. So this is an array. That's not a problem. It's going to be 0 to this. Okay, so then we need an int offset. So this, but we need to subtract x offset from everything. Yep. This minus x offset. Okay, so now it's much smaller. We're not actually creating any. Okay, we don't need this. We don't need, oh, well, okay. That'd be funny. Can you imagine? Okay, we're just gonna have to deal with that. Hash set. I guess this can be an int array. So we can have static long all things and then long array all things. Static boolean contains long array a. Okay, so int min equals 0, max equals a dot length minus 1. Well, min is less than or equal to max. And mid equals min plus max. If a at mid equals x, turn true. A at mid is greater than x, then min equals x plus 1, or equals mid plus 1. But if this thing is too big, then max equals mid minus 1. Otherwise, min equals mid plus 1, and then turn false. Okay. All things equals new long array n. Okay, so this should be quick enough. There's no way they're hacking this in Java. That would be dumb. What else? Scene.contains. What is this? Scene.contains. Oh yeah, so this is what did I call the method? Contains. Yeah, okay. It's up here. Actually, this might be useful. To get hacked. This is a hackable solution, but we're going for it anyway. Okay, let's test it. We changed a lot of stuff. O points is null. Where? Wait, for real? What? O points can't be null. Oh, U is null. Closest. Candidates. Candidates is null? Oh no, I've broken myself. So they're all null. Okay. Yep. Is this gonna break stuff? We shift everybody's x over by the same amount. Shouldn't matter. Oh, it's too small. Okay, but anyway, shouldn't actually make a difference. Okay. If it equals 0. Okay. So help me. Give me a 5-second time limit. That was undeserved. I've been punished for something and I did nothing wrong. This is absolute BS. Absolute garbage. Alright, which one's easier, E or F? Because Rain Boy convinced everyone's minds. Okay. That was dumb. If your time limit's too tight, clap your hands. Let's denote the size of the maximum matching in a graph G is maximum matching of G. You're given a bipartite graph. Good. Maximum matching in a general graph is annoying. The vertices of the first part are numbered 1 to n versus the second part are numbered n plus 1 to 2n. Makes sense. Each vertex degree is 2. Cool. Useful property. So we have some rings of even length. For a tuple of 4 integers, LR, LR, where 1 is less than LR, okay, so we have 2 tuples. Let's define G prime as the graph which consists of all vertices in the given graph that are included in the segment. Yeah, I see. It's hard to explain in words, but I understand. And all the edges are given in the graph such that endpoints belong to one of these segments. Okay, so yeah, just remove everything that's not in the 2 ranges. Okay. Calculate the sum of the maximum matching of one thing over all tuples. Calculate the sum of maximum matching of G, L, R, L, R over all tuples of integers. Oh, so over all possible things. I see. I see. Okay, bit tricky, but there are definitely observations that can be made. In particular, wait, what is a maximum matching? Maximum matching is you match 2 things, so the maximum number of edges you can use. Yeah. So if anything, like, it's very easy to make a maximum matching on this kind of graph. Like initially, do literally whatever you want. You cannot get it wrong. Can you get it wrong? Okay, you can, but like, if you just do it greedily, on each cycle. Like, do it when you can, walk through a cycle, you'll get it right. There are two ways of doing it, which is the two coloring of the edges. You decolor the edges. Ooh. Idea. Let's swap the edges and the nodes. Yeah, that's smart. We still have a graph that's the same thing, but now we are removing edges from the graph. If you look at these edges, what happens? Need more paper. Yeah, the reason we can do this is because man, can you imagine what if I were spending the past half hour on this interesting problem rather than solving a problem that I've already solved? Wouldn't that be nice? Okay, so here's the thing. We've got some stuff like this. I'll do an example here. Partly for the understanding of myself, but also partly to demonstrate that I kind of know what I'm talking about. So suppose we have this graph here. We can instead make, yeah, so what is the cycle? The cycle is very simple. Okay. So we can do this. You do like left side, right side, left side, right side, left side, right side. And then what are the edges? So the edges are, this connects, well, so 1, 2, or wait, 1 is connected by, let's say 1, 2, 3, 4, 5, 6. So 1 and 2 are connected by 2. This is 2. And then 2 and 3 are connected by, 2 and 3 are connected by 3. And then 4 and 5. Oh, yeah, 4 and 5 are connected by 5. But 3 and 4 are connected. Wait, 3 and 4 are not connected. 4 and 5, but also 4 and 3. 4 and 3 are connected by 3. Wait, 2 and 3. 2 and 3 are connected by 3. 4 and 3 are connected by 4. Yeah. 5 and 6. 5 and 6 are connected by 6. And then 6 and 1 are connected by 1. So we wind up with the same graph. But you get the idea. So now we're going to look at all ranges of edges here. Oh, ooh, not quite. So like we have even and odd. So we need a range of even edges and a range of odd edges. Does this make any difference? Probably not. Like, what is the difference? Before we were removing nodes, now we're removing edges. Okay, let's pause this for a minute. The first time you remove an edge from a cycle, it doesn't matter. Well, the cycle's even, right? 1, 2, 3, 4, 5, 6. So if you remove an edge from a cycle, you take this, this, and this. That's fine. But if you remove a node from a cycle, you take... because we're removing two... No. Yeah, you can't use the edge here, so might make more sense to do it like this. So we remove a node. This node was going to be in a matching no matter what, so this -1. But if we remove a node adjacent to it, and this is still -1. But you can remove a node that's like offset by 1. Yeah, okay, so this makes these like, well, still everything is used. No, one thing isn't used. If we remove this, then either this is empty or this is empty. We get one of them for free. In fact, you can get anything in the cycle for free. No, you have to use this, right? If we remove this, you have to use this somehow. But you might get this one for free. So, okay, yeah. If you remove one thing, then anything of the other color, like this is 2 colored, right? So anything of the other color, you can get one of those for free. If you remove one here. So, it's the min of the size of the 2 sets. Min of size of 2 sets. So just have, we can probably do this pretty easily then, right? It's like, we do, yeah, so we're gonna brute force one side, like brute force the left. The left will be, the left will be one set. Okay, brute force left. Oh, then it's tricky, because we have to handle like all of the right in order 1. Probably not too tricky though, because like a bunch of them are increasing. Well, maybe not. Okay, for each cycle, let's consider a cycle, like for a cycle. They are mostly independent. Okay, yeah, all that matters the number of left nodes and number of right nodes? That cannot be right. Yeah, it is. No, it's not. Surely that's not the case. You can have one left node, one right node, still doesn't work. Yeah, there's no way. 2, 3, 4. Okay, so this is one color. So I'm telling you that if we remove, if we have, this is just definitely not true. We can remove this one and this one, that you can get a matching of 2. That's not true. Simply not the case. Okay, so back to the drawing board. I'm not seeing it. How long would it take us to make 1 matching order end time? So my current runtime is like n to the 5. We gotta break down to n squared. Maybe plus a log or something. But not with these time limits. Whoa, Geo popped off. Nicely done, dude. This is very interesting. All right, let me think. I'll be right back. So if we delete 1, yeah, if we delete 1, it can be anywhere. But if we delete 2 from the same chain, we have 2 groups. We gotta have like 1 deleted. We have 1 free one here, 1 free one here. Yeah. And then we're gonna have to use these 2 either way. Why? I don't know. I don't see it. So like, yeah, it's not clear. Like that's definitely not enough intuition to be able to like start solving it. We need more. the problem's still too hard. Data structures can't pull that much weight. Does the number of edges that's there matter? What if we, like if you've got some node, it's got 2 edges coming out of it. One of them contains the thing. So if you have this, this is going to be part of one matching anyway. So that makes things a lot easier. Like, and for a long chain of these things, none of these get updated. Like this is also like part of one matching. So it's like 1/2 really. And this is true for most of them. So then normally this would connect to the old one. Okay. But the problem is now when this, like this was 1/2, but now it gets deleted. It also has to delete one of these 2. Oh, can we just take the sum and round down? That doesn't work. Doesn't work. Well, I guess it kind of works. It's just the length rounded down. It's like the sum of lengths rounded down. Yeah, kind of. Lengths over 2 rounded down. Easier to think about anyway. Because then we don't have to worry about picking things. So we have like a left node has 2 of these edges. This is one type of length. Like that, so that's +1. This is like, this whole thing is like a +1 length. And then we also have kind of the opposite. If you got like a right node has one of these. It's also a +1. It's possible that both of these matter, like in different chains, but not in the same chain. Well, the same chain gets split up, then they both matter later. Yeah, so it is possible. So each of these like add 1 to the length because they're 2 edges, but okay, we also kind of need these nodes here. Like these nodes are important. What I'm trying to do is look at this in some way that would make it like independent per edge. And I think that makes it a bit easier. Because then, like, if we know like how many times this node is important, we can like look at these two things and like evaluate this node in some order fast time. Maybe like handle the overcounts later. Because when we've got these long chains, both sides are important, and then you're not really gonna. Battery exhausted. The camera is plugged in. What are you? Okay. All right. Give me a second, ladies and gentlemen. I suppose more formally, the definition is gentleman. Yeah, not helpful. Okay, I'm gonna be I'm gonna check out geothermal stream here. I guess I'll end this a bit early, but yeah, we'll talk about solutions to A through D here anyway. Probably worth it. So let's do that. 47 seconds left. Okay, here we go. So, problem A, playoff. Okay, in this problem, we have 2 to the n athletes, and they're numbered 1 to 2 to the n. And we have this rule for when a pair wins. So if the sum of their labels is odd, then the lower one wins. And if the sum of the labels is even, the higher one wins. Now, initially, since they're paired up 1 with 2, 3 with 4, 5 with 6, the sums are all going to be odd. The sum of 2 adjacent numbers, one's odd, one's even. Sum of that is going to be an odd number. Which means in the second round, everybody will have odd numbers. And in fact, not only in the second round, but in the second round until the end of the game, everyone has odd numbers. So yeah, it's a bit tricky, but it turns out in all of these games, after the second round and later, the odd person, or the bottom person will win. The person with the bigger number will win, which is just going to be the biggest person who's odd. So the biggest odd number, which is just 2 to the n minus 1, it turns out. So yeah, this is a very, very easy problem to code, but kind of fun to think about. The solution winds up just being this one line here. There you go. This is bit shifting. So in binary, this is like a 1 in binary, and then you move it over by n bits. If you're new to programming, that's what's going on here. So this is the same as 2 to the n. And the logic there is that in binary, right, if you have a number in binary, adding a 0 to it is multiplying it by 2. In the same way that in base 10, right, if you have some number, 43, if you add a 0 to the end of it, that's the same as multiplying it by 10. Because we have base 10, they do base 2. Computers are the they in this case. Okay, yeah, that's solution to problem A. We'll talk about A through D here. I unfortunately don't have solutions to E or F, because I spent a lot of time speeding up D. Also, kind of with a wrong solution to D, but oh well. Prove him wrong. Okay. Recently, your friend discovered a special operation on an integer. You've got choose 2 indices I and j, and set the 2 indices to the absolute value of their difference. Now, your friend claims this will always decrease the sum of the array. Notice how I can read with my eyes closed. Pretty impressive, isn't it? But although your friend says it'll decrease the sum of the array, it doesn't always do that. So an example is if you have the numbers 1 and 10, or let's do 1 and 11. Initially, the sum is 12. 1 plus 11 is 12. But the difference between 1 and 11 is negative. No, the difference between 1 and 11 is 10. The absolute value of the difference. So instead, you can change the array from 1 and 11 to 10 and 10. But 10 plus 10 is 20, so we've just increased the sum. So this is not always true. So what you need to do is see if there is some counterexample for a given n. And it's not always the case. For 512, the answer is no. I guess they're doing this to put powers of 2 in your head subconsciously, because 512 is the power of 2. It turns out it doesn't have much to do with powers of 2. So let's look at the math here. So initially, we have a plus b. We want this to be smaller than 2 times the difference between the two. This is what we're going for here. So if you try a and 2a for the values of a and b, you wind up with the initial sum is 3a, but the final sum is 2a, so it doesn't work. So instead, you can do the math. So if you say a plus b equals a minus b times 2, let's say a is probably going to be 1. That's a good thing. And the question is, like, how big does b have to be for this statement to be barely not true? So that's why we set these two equal. This is the sum before, and this is the sum after. So we don't want the sum after to be smaller. We want it to be bigger or equal. I guess formally it's greater than or equal to. So initially we've got this greater than or equal to, and then we subtract a from both sides. So we still have greater than or equal to, and then we have a less than or equal to 3b. I'm going to switch the sides. So what this means is if we have a smaller number, the bigger number has to be at least 3 times as big as that number in order for the friend to not have an example in this pair. So the smallest we can do is multiply numbers by 3 consecutively, and then all of these things will be true. So every time you go from one number to another, the ratio between the numbers will be bigger than 3. So we can find the smallest example of this by looking at powers of 3. That's what this is. So we get a list of all of the powers of 3 up to 1 billion, and we just generate it. And then we say, are there n of these things? I don't remember how many there are, but there are like 15 or something, I think. Probably more than that. There are more than actually, like 18, 3 to the 18. Did I get that on the dot? I think I got that on the dot. Times 3 will be too big. Yeah. So there are 18 numbers in this array. There are powers of 3, maybe 19. I guess there are 19. There's 3 to the 0 as well, and up to 3 to the 18. So the array's got 19 numbers. We'll print up to n of them, and then that's it. That's the solution. Very good problem. Very good problem. I like it. Cool. Let's move on to problem C, if Code Forces will let us. Now, why is there system testing? That's a question. Isn't there open hacks? No, I guess not. I thought there was you had 12 hours to hack or something. Maybe they decided that's not really very fun. Come on. Okay, I'll just explain the problem from memory then. Fault tolerant network. So here's the idea. We have, oops. Nope. Okay, we've got some computers here, and in one row, Okay. In one row, we've got these computers in a line, and in another row, we also have the computers in a line. And initially, we have the edges that look like this. So all the computers in the top are connected, and all the computers in the bottom are connected. So now we need to add edges to this in such a way that the following property is true. Anytime you delete one node, any node from this, the rest of the nodes are still connected. So it's possible that we could add, I'm gonna not draw it in here, but we could add this edge right here, connecting these two. Actually, let's do this one. There we go. Looks better on camera. My YouTuber side is showing. We can't have that. If we had this edge, that's fine. The problem is if we were to delete this node here, then this would be disconnected from this, right? There's no way to get from one side to the other. So it's pretty clear we need to add at least 2 edges. And maybe we do. Maybe we add 2 edges. Let's say we also add this edge here. Like, I'll just draw it. We also add this one here. We add this one and this one. Those work, but you might see the problem. Problem is, again, now if we delete this one, we still don't connect these 2. In fact, it should be pretty clear that anytime this corner doesn't have an edge, we can delete this one, and that's a problem, right? In fact, more formally, every node has to have degree of at least 2. Because if a node only has degree 1, we can kill the thing that's like its neighbor, right? So yeah, then it doesn't work. So every node needs to have degree at least 2. The things that don't have degree 2 are these 4 corners. And I guess we can say if everything does have degree 2, then it guarantees that we will have a cycle, one big cycle. That potentially visits the same thing multiple times, but it'll, like, if everything has degree 2, every node is part of a cycle. And if every node is part of a cycle, we can delete any node and it'll be connected. Okay, there you go. Also, I didn't mention this, but it's kind of clear from the drawing. Your edges have to go from one side to the other. You can't add an edge between 2 nodes on the same side. Okay, so how do we do this problem? Well, there are a couple of cases. So in general, the thing you might think is connect each corner to the cheapest thing on the other side. That is mostly true, but the problem is there are some edges that are kind of special. So like this edge in particular, if you look at this, if we connect these 2, we only have to pay for it once, but we get both of these corners for free. So this is maybe a good thing to do. In fact, connecting any 2 corners, so this edge here, this edge here, this edge here, and this edge here. Each of those we get 2 corners for, but we only have to pay once. So these orange edges are kind of special. It is not obvious which of these we want to take. But that said, the rest of the edges are only useful if they connect to a corner. So if we know which set of orange edges we're going to take, we're just going to connect each corner to the cheapest thing that it can reach. And that's pretty easy because we can just do that in linear time, iterate through the array, and find the cheapest edge. So in particular, what they guarantee for this problem is that the cost between 2 edges, like each of these purple dots have some number. I won't draw them in, but you get the idea. Every purple dot has some number. And the cost of connecting 2 purple dots is the absolute value of those differences. So yeah, we can just say for each corner, if we want to connect it to something, we find the thing with the smallest absolute value difference. And here's what that looks like. Yeah, it looks really hacky. Here are all the cases. So we're going to brute force which of the orange lines we take. We can take both of them. We can take the other 2 as like an X. We can take the left vertical line, the right vertical line, the top left to bottom right, or the top right to bottom left. Those are the 4 cases. And then we can also take none. No orange lines. So here, those are all the cases. And then I implement them here. So helper methods are A, because math.abs is long, and then maxdiff, or mindiff, which is this thing with the minimum absolute value difference to A. And that is the solution to C. Okay, oops. Yeah, moving on. Problem D. Okay, this problem was absolute cancer. Nearest excluded points. Oh my goodness, this is terrible. Oh my goodness. Problem idea was cool. But the implementation, don't get me started. Okay, implementation wasn't bad. The time limit is what I mean. Time limit was just horrendous. Way too tight. Okay, coordinate plane. Good start. We got a geometry problem. Gotta like it. All right, now we're awake. Now the Codeforces API has returned. So we've got some points that we're interested in. Maybe they give us this point here, this point here, this point here, this point here, this one, and this one. So what we need to do is for each of these points, we need to find a point on the Cartesian grid that is closest to it by Manhattan distance, which isn't one of these purple points. Now, the points they give us all have positive coordinates, but the points we return don't necessarily. So as an example, for this point here, we can return this point, and that would be one possible answer. If there are multiple answers, we can print any of them, and we have to return the answer for all 10 to the 5th points. So the bounds are pretty big. So we're going to need some sort of fast solution, like an n log n solution, or if you use Java, an n log n solution after you have bonked your head into the ground 45 times. Anything less optimal will TLE. So, okay, yeah, here's the idea. So first, let's take a look at this distance function here. So if we have some point, the things of distance 1 away from it will be like this diamond of distance 1. So it's the sum of absolute value distance in x's plus y's. So like d1, dx plus dy. Distance 2 is this. So this is, you can think of this as like the diamond distance. They call it Manhattan distance, but I think diamond distance makes a bit more sense because they look like diamonds. There's also square distance, which is, square distance is that, so that's diamond distance. And there's also circle distance, which is draw circles. And there are other types of distances too. Sphere distance. Circle square distance. Okay, anyway, I'll stop. You get the idea. So here's the distance metric. One thing you could try that doesn't work, but I'll explain it just because it's important to know, it's easy to get wrong, is you might think that, okay, so we're trying to get the closest thing to each point, right? You might think the closest thing to this one is going to be the closest thing in this direction, closest thing in this direction, closest thing in this direction, or closest thing in this direction. Problem is that's not true. So let's imagine the closest point to this point is like, let's say it's this point right here, or let's say it's this point. So ignore this. So this is the closest point, and the diamond this fits in is this diamond here. But this is the point that we're going for. We can break it. So the way we do that is we can add a point really far out here, 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 and here. So obviously, none of these green points are very close to the black point. And obviously the closest point to the black point is this purple one. But it turns out if you look in this direction here, the closest point to this black point is this one here. And if you look in this direction, closest point to this black point will be this one here. And in this direction, the closest point to the black point is like this one. And in this direction, closest point to the black one is this one. So in all 4 directions, the closest point to the black one is one of the green points, which is actually really far away in the other dimension. However, the right answer would be the purple one. But if we only check these, we're going to miss the purple one. So this is an easy way of getting the problem wrong. So how do we actually do it? Well, as some guy whose name starts with S and is, I think, Polish said in a comment somewhere, as he once said 6 years ago, the way we want to do this is, the problem is that we're looking at the distance metric in this dimension, which is fine. But the issue is that when we do this, when we look at the distance metric in this dimension, we're considering things that would use a different distance metric. So, like, this point here is getting counted as being bad, as being worse than this point here, which by this distance metric it is. In this direction, this point is farther away than this. But the problem is, any of the points in this quadrant are using a different distance metric to be evaluated as. So we can't include this, like these points, as the optimal candidate for this direction, because these points are going to be judged by this instead. So what we need to do is we still are interested in the first point in this direction, but we only need to look, or we're only allowed to look at things in this quadrant. So things with a bigger x and a bigger y. Now, doing these 2D queries is pretty expensive because it requires a 2D segment tree, and you'll TLE for sure, even probably in C++. So yeah, don't try doing a 2D segment tree. It's going to be too slow. Instead, you can do these queries offline. So we know we're going to have to solve this for every query in all 4 of the directions. So for one point in one direction, we're just saying, okay, we need all of the stuff in this dimension. So we can do a sweep through the points. We're going to sweep down, check the points by y. So all of the points that we have processed will be above this line here. They'll all be above this. But we might also have some points like over here, and we don't want to be including these points when we do this query for this point. So what we can do is we can have a segment tree on these x coordinates. And then on the segment tree, we'll query everything that's over here. So we'll say, of the points that are to our right, but also, like, there's a secret, like, of the points that are not only to our right, but also are above us, we're querying those. Of those, we want the first one. So the one that crosses the first line like this, the first diamond. And that'll be this point here. Now, this metric works for all of the points. We're going to use the same metric. So we're always interested in the bottom leftmost point. In fact, we're always interested in the leftmost, or in the bottom leftmost point, I guess, in total. But we're interested in it for every x range. And since we're doing a segment tree, we can query for any x range what is the bottom leftmost point. And then the y's are taken care of by the fact that we're doing a sweep. So we're only considering stuff which has a y that we already know works. Okay, that's the idea. On top of that, it's just super tight time limit. Maybe they were afraid of like a n log squared or something, I don't know, but to me it seemed way too tight. So things you need to do in order to optimize. Step 1, you need to make sure your segment tree is as tight as possible. So it's got to be only 200,000 wide. Not 400,000, not 600,000, only 200,000. Or I guess 200,001. So that's got to happen. After that, you need to not create any extra array lists that you don't need. You only want the array list that you've got. Okay. After that, what else? You need to make very sure that you are not using any tree sets anywhere. Make very sure you are not creating any objects you don't need. And next option, you have a choice for this one. There are 2 things you can do. One, you can either, here we go. Nobody cares about the screen. So the last thing you need to do to speed up your code, you can either choose not to use any tree sets and instead, or any hash sets even, instead you put all of your objects into integers, sort them, and then manually binary search every time you need to see if there's a duplicate. That's one option. Option 2 is ignore everything I just said and switch to C++, and I'm pretty sure it works. So yeah, there you go. Those are your choices. Okay, so what does the code look like? Well, kind of trash, if I do say so myself. Here's the idea. So this is literally just a hash set, but you need to do it so it runs fast enough. And this is like, see, we're doing these bit shifts. It's lots of shenanigans. We are, this is to check if a point exists, and I'll talk about why we need this in a minute. But basically this is just like, in the sorted array, does this X thing appear anywhere? So we do a binary search to check if that works. Implementation's not too important because it's dumb, you shouldn't have to do it anyway. But yeah, okay, so this part is we store all of the initial points, and then, I didn't even mention this. Okay, important part of the solution, there are 2 sets of points. We have all of the points initially. The other set of points is all of the points which are 1 away from that initial set and aren't in that initial set. Those are the other points that are interesting. So yeah, so you can imagine like red points and blue points. For each red point, we need to find the nearest blue point to it. Yeah, and we're gonna do that with like some segment tree shenanigans, like I just explained. So this is to get all of the blue points. That's what we're doing here. So we look at all of the things that are offset by 1 from one of the red points, and those are going to be all the blue points that are interesting. And we add this to our array list if it doesn't already exist. Okay, now this should just be an array list, but instead it's not. We have this array of all of the points that are both the red points and the blue points. We're going to do a sweep through this in just a minute and keep track of some stuff. So this makes it a little bit cleaner. What I'm doing here, I have this method to rotate all the points by 90 degrees. And this way, I don't have to actually code 4 different sweeps. I'm just going to code 1 and then rotate the entire grid by 90 degrees. And I'll just do this 4 times. So I'll do it once in one dimension, rotate everything, do it again. And then at the end, I'll have consider all 4 directions. So yeah, that's just makes it a little bit cleaner. Less copy paste, especially if you have bugs in your code, then you have to fix them 4 times. And then not fix them in one of the places, and then you're very confused, and this problem is very hard to debug anyway. So yeah, that's the idea. Okay, so what are we doing here? Okay. Yeah, this is cancer. So segment tree can't include both positive and negative numbers because that's too slow. So instead, we include only positive numbers and are shifting this thing around just to barely get it to work with 33 milliseconds to spare. It is that tight. I know. Yeah, absolutely insane. Don't use Java, ladies and gentlemen. So yeah, this is what we're doing here. We're getting this offset. This offset is equal to the thing with the smallest x coordinate. We sort the points by x and then y, so we can do our sweep. This part is important. You can't just sort by y because you need the stuff with the same y as you, but that's after you in the array. You need that to come before you in the sweep. So that's why this line is important. The second line, can't forget it. Okay. Yeah. Then we go through all the points, do some stuff. If it's blue vector, then its ID will be -1. So we add it to the segment tree, and if it's not, then we find the closest vector to it, which is the first thing in this valid x range. And then this is more cancer, but it's to get rid of extra array lists, we add it to our list of candidates. This should just be adding to an array list, but it's not because things are so slow. Okay. What else is important? So I clear my segment tree rather than just make a new one. Again, it shouldn't matter, but it's a time limit thing. I do this rotating thing here. Yeah, and I guess that's it. Okay, yeah, that's solution to problem D. All right, so that's A through D. Hopefully you enjoyed. That's all from me. Geothermal should have solutions to E and F if you're interested in those, but also those are in the editorial and might be good to upsolve. Okay, if you're in Div 2 and this was rated for you, hopefully you enjoyed the contest. I thought it was a pretty good one. I liked all the problems. And if you're a problem writer, please just give us some more time. The time limit was so small. Okay, yeah, anyway. That's all. Thanks for watching. Have a great day, and get out of here. I'm getting pinged from work. All right, goodbye.